Yeah. That's fine. Yeah. He was working but all changes small minutes experience what is not unfortunately.
Hello?
Okay.
Hello? We have one more homework due, which will be 2 weeks from today. That means within 1 week of classes, basically. That is, next week is holiday. After that, we have 1 week of classes, then we have 1 week of exams. So that's our semester. We have 2 more classes than this. Yes, after today, we have 2 more classes, Monday and Friday of the last week of classes. And the exam, and then the exam. So I think it's there will be a homework 11 that will be due December 5, Friday, and then that is the final exam. Which is 3 weeks from today. But from 8 to 10. And we also agreed upon a breakfast. December 12, Friday, 10:30 a.m. This is optional. You don't have to. Tell it again.
I'm just kidding with them. No grading for that.
No grading. Yeah, both positive and negative, right? Like, it's easy to think that, oh, how will someone deny a breakfast? But then I think I noticed that many people don't stop. They prefer to be not there in public, maybe. So don't feel compelled. That's anything. Is there anything else I'm missing? Yeah, I think that's all. We have. Any feedback from you guys? Like, this is 1 more week remaining. Anything else is productive?
Yes.
Yeah, so we still have a lot of things to do, but within the time constraint, I've decided to just, we have mostly spent time on spherical coordinates. How typically it comes up is that we do this at the end. You start with cylindrical coordinates. Often it is significantly simpler. and then come to spherical coordinates. But I did the opposite. And I did feel that it is more intuitive because whenever you do cylindrical coordinates, you have to do planar geometry. And planar geometry has this disadvantage that you have to go all the way to infinity. So that's a bit unrealistic, and that takes away a little bit of intuition. But spherical geometry has a feature that it's a sphere. We can think of multipole expansion in that sense. And I felt there was a little bit more intuition we could associate with spherical harmonics than what we are going to, what I usually do. This is relegated in the end of the semester and we don't get enough time. So this is the first time I switched the spherical coordinates compared before cylindrical. And so now cylindrical coordinates suffers for that. We have only 1 week to do cylindrical coordinates. So I'll do as much as I can. But almost everything that we did for spherical harmonics can be done for cylindrical coordinates. It's often called cylindrical harmonics. And the functions we will need for that is called Bessel functions, which probably you have heard of. How many of you have heard of Bessel functions? Yes, okay, everyone has heard about it. So, so that's what we will do. And it was, if we had enough time, we will be able to show that spherical harmonics in some limit leads to Bessel functions. And can you imagine what limit it would be? If I say a sphere, the geometry of a sphere is associated to spherical harmonics, and geometry of a plane is associated to, let's say, Bessel functions, then what might be the limiting condition in which spherical harmonics will lead to Bessel functions, let's say? What's the connection between a sphere and a plane?
Open it up.
Open it up? No.
No.
Then you're taking away the geometry. Some other thing? Very good. So if you take the limit r tends to infinity, flat earth scenario, a flat earth is in a limit r tends to infinity, which is roughly like opening, but it is more than that in a sense that you still keep the fact that it is a closed geometry. And we can show all that. We can show from spherical harmonics and show that in the limit r tends to infinity, it will lead to Bessel functions. This is an immediate thing. But I suspect that we won't have the time to do that. So the idea is that first we have to do Bessel functions, then do modified Bessel functions, and then you see the limit coming up. Unless you take, I go too hurried. So again, the geometry is that we are going to do flat geometry instead of a sphere. Think of a plane wherever you see a plane. Whatever we are doing is applicable. That's the best intuition you can have. But for our purposes, we will start over every time we have done spherical harmonics or legendary polynomials. We started with the 1 over r potential, right? Potential due to a point charge. That's what led to spherical harmonics. So we will start again from the 1 over r potential, the electric potential due to a point charge, or the gravitational potential due to a point mass, and then try to do this for a flat Earth. Again, flat Earth is a good example. There's a connotation associated with the idea of a flat Earth, but that's practically what we are doing. Okay. So broadly, cylindrical harmonics can be our cylindrical harmonics, but more specifically Bessel functions. So before I reach the idea of Bessel function, I'll take the spirit that I have been trying in the last 2-3 lectures. What we did is I was trying to introduce Green's function also. We didn't get, or at least after grading your homework, I got the impression that you haven't got too much experience in Green's function. So what I did was while I was doing spherical harmonics, I motivated the idea of Green's function also. So I'll begin with that idea here. I'll again try to write a Green's function in cylindrical coordinates this time. And again, associated with the fundamental Green's function is the electric potential due to a point charge. Right? That's a at least for our purposes, the fundamental Green's function. But every differential equation has a Green's function. So I'll start from there, get a Green's function, and starting from there, I'll introduce the Bessel function. So it's opposite of what we did for spherical harmonics. There we introduce the spherical harmonics and then discuss the Green's function. So let's start with the point charge. So point charge, what's the electric, or what should I say, charge density due to a point charge? Charge density due to a point charge?
4 pi rho delta.
Rho, no. So specifically, I think I heard it. Rocky?
That's rho.
Rho? But rho is just some charge density. I'm saying point charge.
Like 4 pi delta 3.
Yeah, delta function, right? You said rho.
Is there not a rho in it? Like
No,
the charge
rho is the charge density. I'm asking you for the charge density.
I just said okay.
Right? So I heard the charge density, so I said I didn't even hear after what you said. So sorry.
That's okay.
So maybe that's what you meant to say that it's a delta function. So probably what you were probably meaning is that you were saying 4 pi rho. Now that I'm trying to think, is that what you're saying?
Yes.
But that has the wrong dimensions, right?
Yeah.
One charge over density, charge like this is q over L cube. This has 1 over L cube, so it's q over L raised to 6. Just to argue, make my point.
Yeah,
But I see. I think, but if you had the delta function in your mind, that's good. That is all I was looking for, right? But it's not rho. You want something that when you integrate gives you the charge, so it should be q. So it should be q. That is no 4 pi there, so it is q over just q. That's it. Right. So the charge, point charge, the charge density. Maybe I can write it rho would be q times delta function. And it's r minus r prime, where r prime is the position of the charge. Right? Good enough. And that's true that it is, how do you verify that? Charge must be equal to integral of rho, right? Integral of density should be the charge. So I put in the q there. Q times delta function of r minus r prime. Even if the charge moves around, it doesn't matter. This will always integrate out to q. If I integrate over all space, somewhere at least at one point there is a charge in there, it will always catch that. So r minus r prime is not relevant. So charge density is for a point charge is this. What is the electric potential for a point charge?
1 over 4 pi epsilon naught.
Good.
1 over magnitude of r minus r prime.
Q over 4 pi epsilon naught 1 over r minus r prime.
Yes.
Good. So that's our. So this is the electric potential. But if you write this as a differential equation, use Maxwell's equation. This satisfies the the Laplacian or no, or Poisson equation. So that's minus del square times phi is equal to charge density for any charge density that is true. So if I were to plug this in, the q cancels out, and what is missing here? Is this correct?
There should be an epsilon.
There should be an epsilon naught. So very good. So this is epsilon naught. I'll write it there. And then immediately you see that you get a differential equation. Del square 1 over 4 pi times 1 over r minus r prime is equal to a delta function. And whenever you have a delta function alone sitting on the right hand side, that's called a Green's function equation. Any differential equation, if you have a delta function on the right side and a differential equation on the left, then it's called the Green's function for that differential equation. So this is the Green's function. We know the solution already for the Laplacian. So the point charge electric potential due to a point charge is the Green's function for the Laplacian. That's a statement we have. So explicitly write this down. So we have d by dx square plus d by dy square plus d by dz square. Explicitly, this is equal to 1 over 4 pi of 1 over x minus x prime square plus y minus y prime square plus z minus z prime square all over a square root. That's what this magnitude means. Right? This is equal to delta of x minus x prime, delta of y minus y prime, delta of z minus z prime. Right. That's what it means. What we did while we were doing spherical harmonics is, I was interested in the geometry of a sphere. I wrote this equation or the differential equation in spherical coordinates, and then the radius I was trying to solve for. This time I want to keep the cylindrical coordinates intact and do everything in that spirit. So for that, how do I go in that direction? So let's say this is a plane. So you have a planar geometry. So that's your plane. And let me choose my z hat axis in this direction. Let's say k hat. Sometimes I use z hat, k hat, z prime hat. All of them are the same direction. This is perpendicular to the plane. If it is a uniform plane, if there are no corrugations on the plane at all, Christian?
There should be a, in your square root there should be a square on this.
Square, yes. Thank you. Thank you, that helps. Yeah. Any other comments? So that's an explicit expression. I can work in any coordinates, right? We tried to work with spherical coordinates last time. Now let me try to do this for planar geometry. And I'm having the physical system I could have is that the plane is really uniform. That means to say that whether I stand here or there, my universe, my system doesn't have any difference. It is like saying, whether I stand on the North Pole or on the South Pole, the sky should look the same. It doesn't look the same because we have stars around. Imagine a situation if there was no star at all, like it's complete vacuum. In which direction you stand on the Earth, it shouldn't make any difference. You won't be able to make out any difference between where you stand. So that will be called spherical symmetry. Same thing here. We stand anywhere on this plane, system looks the only difference you can see is that one is on the other side, one is on the bottom. That's the only difference. Like in a sphere, we could have said one is inside, one is outside. That's the only difference you can make out. Otherwise, it is spherically symmetric. So that's the symmetry we want to use. And in the planar direction, so this is your plane. So that's z hat or k hat, I said. So that's your k hat. And there is an x and y plane, right? So x and y is in this direction. We will call this, so a vector r will be denoted as z times k hat. Let's not say k hat because I'm going to use k very soon for other purposes. So z hat, let's say. So z times z hat plus whatever vector remains, I'll call that r per. It's basically x and y, so it's pretty straightforward what I mean there. So our curve is going to be equal to x hat plus y hat, or xi hat plus yj hat. And it doesn't even have to be in any of these rectangular coordinates. I can also say this will be a row hat, like just row, right? So the vector row itself is sufficient, which is equivalent to saying that this is rho cosine theta in the I hat direction or x hat direction plus rho sine theta. I'll use phi actually, phi in the y hat direction. These are different coordinates I can use in the xy plane. These are cylindrical coordinates, but we are splitting. Surely the z direction is being stripped or treated separately from the xy direction, because we're saying that xy direction has a symmetry. In those situations, it is convenient to, whenever there is a symmetry, you want to use some transformation to get rid of that. Whenever it is spherical symmetry, you use spherical harmonics. Here, if it is in the z direction, and especially if there is symmetry in the xy direction, let me use Fourier transform in the xy direction. So this function here, let's call that the Green's function. This will be that's just for compactness. I'm doing this. So this is r, r prime. This is the most explicit way you can write that. But I would have, just for compactness, I want to write that as g of r, r prime, which clearly has the structure x minus x prime, y minus y prime, and z minus z prime. If there is symmetry in the x and y direction, x minus x prime will stay. But if there is no symmetry in the z direction, which it doesn't because there is a plane there, so we will lose the z minus z prime in there. So in general, function might not have it, but Green's function is still z minus z prime. So let me just write it as z minus. In general, this may not work. I'm saying if there is a planar jump. Whenever we have this structure, we can Fourier transform this. So let's Fourier transform this in the following way. We have a Fourier transform in the x direction. So that is Fourier frequencies coming in. That's 2 pi times e raised to I kx, x minus x prime. And then Fourier transform in the y direction. So that's ky over 2 pi e raised to I ky in the y minus y prime direction. So both these frequencies associated, frequency means in this case it's wavelength, right? Wave number, you will say. So wave numbers associated with the x and y direction is kx and ky. And whatever are the coefficients, so these are the Fourier eigenvectors you want, eigenfunctions, whatever remains, we will call that G. What does it depend on? It can depend on z minus z prime. Let me write that as z comma z prime. It doesn't matter. And we have kx and ky. So what are these small g that I have returned? These are the components of this Green's function in the Fourier space of x and y plane. If you want to expand that in terms of the Fourier transform, then that's what you'll have. You can make this compact a little, exactly the same thing, but usually you shorten this. It's pretty much like saying G. But the moment you write G, it is compact, but then you lose the explicit nature of that. Intuition is lost. So at that same spirit, this is d2k. Just for compactness, it is d2k per 2 pi whole square. This is exponential I, the vector k per, dotted with r minus r prime per. And then there is g, z comma z prime. And this now becomes the vector. I've used the fact that K perp and R minus R prime, you can write it as a dot product. So if you're in the X and Y plane, your J hat, that's your I hat, that is a vector K perp here. And that is a vector R perp here. And there is also a vector, all these can be in different directions, R per prime. These are the three vectors we have in this picture, right? And K per dotted with R minus R prime per, or you can say perp outside, is basically Kx times x minus x prime plus ky y minus y prime, right? That's just a way of writing this. That's what we mean. But in this plane, this looks like r minus r prime. I have to subtract that, which will stay in that plane, and then take a dot product with k per. Right? And this figure will come out important once we choose this, like we had spherical harmonics. If you choose one of the angles on the north pole, then it becomes legendary polynomial. Similarly, when you choose r prime along the x-axis in this case, then that will be simpler. Oh, I used I hat in the vertical direction. That's not common, right? So it doesn't, that's just because I was motivated with the spherical harmonics. Let's keep the standard thing here. So this is I hat and j hat. That's more standard, right? But this doesn't matter at all. So that's all I have done. I have Fourier transformed my Green's function. I could have Fourier transformed any thing that has three parameters and three coordinates in it, and if that is xy, I can do this. The idea is, how does this differential equation change? What you would do is you will substitute this in there, operate this differential operator, and do that. But we have already done this. I think there was even an exam question. Differential equation in Fourier transform, just the derivative you replace with k, right? That is all you have to do. So we have learned this better. So d by dx gets replaced with I times kx. Whenever, if I substitute this in there, d by dy gets replaced with I times ky. And delta function, so pretty much if I were to say del perp, right? This is another language you will start seeing. I hat d by dx plus j hat d by dy, right? So that's only the x and y component to that. So gradient operator practically means I times k perp. Be careful with I. I is showing up as I hat, and the complex imaginary or what is it called, square root of -1 is I here. So here I is square root of -1. I hat is the unit vector that we have. So that's here, and we also need the fact that a delta function x minus x prime is switches to 1, and delta of y minus y prime switches to 1. So in a differential equation, if I do all this together, then that's all I have to do. I don't have to do the algebra quiz. Do this explicitly. Whatever I'm going to do in the next step, explicitly do that. So that's an exercise for you. So I will get my differential equation as, I start with d by dx, ikx, that's twice. So that's square of it, plus iky, square of it, plus d by d square, dz square, I keep it intact. And g becomes small g, the Fourier transform, g, z minus z prime if you want, and that's equal to 1. Sorry, delta of z minus z prime remains. And rest everything becomes 1. So that's the question. Yes.
So what do you want the quiz to be? Like, do you want to?
What I did is I pretty much read out this, right?
Mhm.
Explicitly do this, you substitute this in there, then you have a derivative operators coming into the integral. You have to use the completeness relation of the Fourier transform to show that there is a right-hand side that is a integral, left-hand side that is an integral, and you pick out the coefficient. So it's a tedious work in the sense that it might take some 5 or 6 steps, but there are some, let's say, important concepts you use, basically the completeness relation of a Fourier transform. But I am using the poor man's Fourier transformation, who doesn't understand Fourier transform. Like I'm pretending I don't understand, I'm just going to apply the Fourier transform. Is that clear what is required? Excellent, right?
Yes.
Right. Okay. No. Okay. So my differential equation now becomes straightforward. This is a one parameter differential equation, often easier as an I square. So this is kx squared plus ky squared is k perp, right? So kx squared plus ky squared is the magnitude of k perp. So I will just say this is k perp squared. When I don't write the vector sign, it means the magnitude of that quantity. Magnitude is always positive, so I don't have to worry about it being negative. So this is k perp squared, and that is a minus, and that is an overall minus sign, and that's my differential equation. And this depends on the vector k perp. In fact, it depends only on the magnitude. So it's k perp in a sense. That's equal to delta of z minus z prime. So that's a one-dimensional differential equation. Not only a differential equation, it is a Green's function equation because it's a delta function on the right side. So that's a Green's function. We can solve for that. What are the initial conditions you will use for that? So usually in a Green's function, there are two conditions. What are the physical boundary conditions? So physics requires that, or some outside requirements require physical boundary conditions in this case, not initial conditions. If it was time, then you say it is initial conditions. These are in position, so you call it boundary condition. So physical boundary conditions would be that the Green's function has to be going to 0. This is an electric potential we are talking about. It should go to 0 when z is infinity. It should go to 0 when z is minus infinity. At both extreme ends, they should be 0. So you can say that g of infinity, comma z prime, comma k perp is equal to 0. It should be limit z tends to infinity. That's one condition. And the other is that it is minus infinity z prime k perp is equal to 0. That's a physical boundary condition. Usually, a Green's function also has continuity conditions at z equal to z prime. So, continuity conditions. Always, if it's a second order differential equation, there will be two continuity conditions. What are the, at least let's begin with one. What is the continuity condition for the Green's function? How do you go about that? Tell it again.
You just take the derivative of the Green's function.
Not derivative, you meant
Integral,
integral, right? You meant that. Very good. So we take the integral of the Green's function around z prime. So we take an integral because there's a delta function. Somehow you want to treat the delta function. What is the contribution to that? So that is a z. That is a physical parameter, and at z prime there is something special happening. The source is there only at z prime. That is what is disturbing the symmetry in the z prime. So that's your z prime. So there is something happening before z prime, something happening after z prime. So we integrate out, and that should patch up right there. So we integrate this equation. So around z prime or z equal to z prime minus epsilon, let's say. This is epsilon, has nothing to do with permittivity. That's just a small positive number. and this is partial derivative of second derivative of z square times g, and plus k perp square times integral z of g, same idea, z prime minus epsilon, z prime plus epsilon. And on the right side, as far as you capture the pole of the or the divergence structure of the delta function, if you're around z prime, it will always contribute. So even if it is small, it will contribute. So that's equal to 1. And now you say that how can I satisfy this? One has to argue that there are more concrete ways of doing this, but one solution is that this is g is continuous and the derivative of g is not continuous. So the continuity condition is first is that the derivative. So you said this is 0. So g at plus and minus. By plus and minus, I mean the upper limit and the lower limit. That's equal to 0. So that's continuous. And the second is that derivative of g plus or minus, and it is negative of that. So these two terms has to contribute to 1 to this. So that's and there are more possibilities you can think of, but that's that's at least one continuity condition you have. Once you have this, then you can immediately proceed and get your Green's function. Any questions until at this point? So, and I think this was also part of one of your homeworks. Yes. Yeah.
Could you remind me why g has to be 0?
The first one, yes. So notice the differential equation we have is second derivative of g plus g, right? That's plus g has to be equal, and that k perp square is equal to delta function. Overall, that's what it is. Let's say that g was not continuous. So let's think of this to be your Green's function. What that would mean is that its first derivative, so this is your g at this point, so that's your z prime. At z prime, the derivative of g will already have a delta function. And you can visually see that there will be a delta function. So this will be having a delta function. So that means second derivative of g will have a higher derivative of delta function, which is not what I have here. Okay. Only way to escape that is to so you can say that its derivative is continuous, but g has to be continuous. Like derivative has a discontinuity in here. So if this was g, the derivative of g would be having a discontinuity. So then this will be having something like this, and then I get a delta function. Okay. And there are various possibilities there, but that's okay. But this is the primary argument that it cannot have a discontinuity in there, because then the differential equation will have higher derivatives in there. Like reasonable? Right? So that's and this can be made more concrete, but it is like in a lecture where I'm trying to do something else, I don't want to go there. But if it was an explicit calculation, then I can spend 15 minutes to derive this second relation. Okay, so we have now two boundary conditions coming from here, and two continuity conditions and two boundary conditions. So your Green's function has the structure g of z comma z prime. Let's say k perp is equal to a times what is the solution to the left hand side? If it was a delta function, if it was 0 on the right hand side, what are the solutions for this differential equation? If the right hand side was 0,
e to the k perp z.
E to the that's correct. There is no oscillatory. If it was second derivative of z square plus k perp square, let's say f is equal to 0,
Then it'd be sine.
then it is sine and cosine. This is harmonic oscillator, right? Then it is exponential of I e raised to I k, let's say z, right? Plus or minus. But if it is minus, so if it was second derivative of z squared minus k per square with a negative sign if you want, f is equal to 0, then these are the hyperbolic solution, cosine hyperbolic and sine hyperbolic, or you can say k per c, right? So either they are growing exponential or they are decaying exponential. That's your solution. So that's anytime you're told that this is the solution of something, you just start to substitute and check it. Right? You don't have to derive it. So those are tricks to do it, but whenever it's a differential equation, if it satisfies that, that is all you need. Right? If it satisfies this, you're just verifying it. At least it is a solution, and that is all we are interested in. So if z was not equal to z prime, there are two possibilities. Either it could be 0 from the left side, so there is a solution on the left, solution on the right. So I can say this is e raised to I, let's say plus growing solution k per z plus b times exponential of minus k per z. And this is if z was less than z prime, and I have c times e raised to plus k per z plus b times c prime plus it. So z is greater, so it's on the right side. Good. So anytime you have a Green's function, that is how you proceed. You write a solution on the left, you write a solution on the right. Each of those solutions are the solutions to the you call a free Green's function. That means it is 0. That means the homogeneous part of the differential equation whenever you set that to 0. And then there are four constants, 4 arbitrary constants at this stage. We have 4 requirements, right? 4 boundary conditions, they fix them. So at plus infinity, when z is very large, this has to be 0. Right? When z is very large. When z is very large, that will be here, right? Z has to be very large, so it has to be on this side. And it has to be 0. If this piece exists, that cannot do the job. So this must be 0. That's 0 because this condition has to be satisfied. Do the same thing at minus infinity. When z is very large on the z negative direction, this is what blows up. So that has to be equal to 0. Is that clear how I'm doing that? So that we do that in standard partial differential. Next comes the continuity conditions. So these two have to be the same. So g plus and g minus at z equal to z prime in the two directions, they should be the same. So that also means that A must be equal to D, right? At z equal to z prime, because this is using g plus is equal to g minus, right? If at z z prime, like this is equal to x z prime, helping, is that correct? Probably not. Okay, let's do that. Let's proceed. So let's do these two conditions. Let me do derivative of g. Maybe a is not equal to d. I'm slightly confused. So it is k per a times exponential of plus k per z, and this one is minus k per d exponential of minus k per. So this is z less than z prime less than z. Put the two conditions. The plus is when z is on the right side, so that's in here. So d times exponential minus k per z prime minus a of k per z prime is equal to 0. So g plus minus of g minus evaluated, that should be continuous, and the derivative should be equal to 1. So derivative is this, evaluated at but I have to do the minus of that. So it is d times exponential. So minus of this. Hopefully, I'm doing this correct. So and paper. Oh, paper. Yeah, I'll keep the paper from the right side. Minus of that. Am I doing correct?
Yeah. That should be 1/k. So
I'm doing it. Okay. There's a minus and a minus that becomes a plus.
and there would be another minus.
Yeah. Right, and this will be having 1/k per. That correct? So like there is a minus sign with a minus sign, so that's this here. And a minus with a minus sign. Oh, then there should be a minus sign.
There's a minus.
No, minus. There become a minus and a minus sign is plus. Minus.
Yeah, there'd be a plus because there would be a minus from the evaluation, but then there's a minus outside of that turns it into a plus.
That changes into a plus. Okay, so that's correct, right? Okay, thank you. Okay, so now we can solve for this the determinant or d if I'm interested in. So d is equal to the denominator comes out to be this times this, which is 1. This times this is again 1 with a minus sign, so that's factor of 2. Put that when I'm evaluating for d, I have to substitute this in here. So it is plus 1/k power times exponential, and these two go away. Oh, k power, so this is k power d prime. So that's equal to 1/2k power exponential of k power d prime. Let me check. So that's in here. So yeah, so let's see from. And a similarly would be equal to 1/2k power. And I substitute this in here, so it is minus k power z. I think that's good. Okay, so we pretty much have our Green's function. This is z comma z prime k perp. It's equal to a is 1/2k perp, and write this as as say perp, yeah, k perp of 3 minus z prime. So v is less, so it should grow. So z prime, I should write this. So whichever is greater, I write that z prime minus z. That's your Green's function, which can be captured in a compact form as exponential k power z minus z prime. So that's your Green's function. All that to clarify that, yeah, I wanted to introduce the idea of Green's function once more as an example in the classroom. But once you have that, you go back all the way and say that, oh, okay, in this Green's function here can be written in terms of this in that form, and that is where we will introduce the Bessel function. That's what we will try to use to follow Bessel function. But before I proceed, any questions on this? This is mostly on Green's function. this is pretty much the Green's function for a plane. Anytime you do reflections, most of you do optics. I think you will see this will be this is how you will derive reflection coefficients and transmission coefficients. Yes, today whose talk is going to be discussing this. So yes, good. Okay. So let's go back and yeah, so we have this as our Green's function. Come back to this stage. Okay, so with this diagram and this as your Green's function, what we have shown is, explicitly speaking, is write this down. So this is your 1 over 4 pi, right? So 1 over 4 pi times r minus r prime is equal to dq of dqk over 2 pi whole square e raised to pi r started with r times exponential of Green's function here is this e raised to by 2 r. Right, so that's a representation, if you want. That's one way of writing a simple 1 over r potential can be expressed in that form. This is on a plane. This is the z direction. We have pretty much separated your z and k direction. If you want to see it more explicitly, these are Fourier transforms. Remember, these are Fourier eigenfunctions. If you recall your spherical harmonics, we wrote YLM and YLM. So this is exponential ik per dotted with r. And then again, there is a minus the complex conjugate of that. And another point times exponential it's good to compare this. So recall how we did this in like I'll just write it and then probably or maybe do this a little below. So this is the same thing, same 1 over r potential and spherical harmonics. What we did was first we did L equal to 0 to infinity. Instead of Fourier components, we were adding the angular momentum components, L equal to m, and then we did the m also. This is m equal to minus L to plus L. So instead of the Fourier kx and ky, we were having this. And what we had was y lm theta comma phi. So that served as your, so this is your Fourier eigenfunction, spherical eigenfunction here. The conjugate of that, the completeness thing going up. That was star, that's a complex conjugate of that. And whatever showed up here was the Green's function. And it was, first of all, there's a 4 pi over 2l plus 1. That shows up in the spherical coordinates. And instead of z minus z prime being less and greater, here it was radial, right? It was a sphere. For a sphere, it is outside the sphere versus inside the sphere. Here it is exponential because you have to decay it. So here it was the exponential that is decaying. Here it is a power function. Like, is it growing as as r, or is it decreasing? So this is the one-to-one correspondence if you want Fourier eigenfunctions, spherical eigen functions. That's the one-to-one correspondence in that. But with that intuition in mind, we are that's not really needed. It is explicitly, it will come out to be so everything that goes in spherical coordinates has a relation in here. So we want to do cylindrical coordinates. So we want to process this, not this. That is the z direction. We want to process the cylindrical eigenfunctions in this case. So what we do is let us choose. Let us yeah. So yeah, I don't even have to choose k per. So yeah, k. Yeah, k per is equal. Or let do this. Yeah, k per dotted with that's all I. So dotted with r minus r prime. Right. So that's going to be equal to, let's say, magnitude of the vector k, magnitude of r minus r prime, per, and the angle between them, which I will say is cosine alpha. Remember in, yeah, I should have written this down more. Let me write this down again. Stop. Okay. So I think comparison helps. R minus r prime is equal to L, that is M, and there was YLM. Theta phi is practically a unit vector on the sphere. Right? Theta phi is a unit vector for sphere. The other one is YLM R prime. And that is R less, R greater. And in that sense, you will see that this has this feature that R hat dotted with R prime. How much is that equal to? R hat dotted with R prime, that showed up in your quiz here. Most of you calculated that. Yes, so cosine theta, very good. So cosine theta prime plus sine theta prime, and cosine of phi minus phi prime. Yep. Often you say it is cosine gamma, right? So this is cosine gamma, and if you choose theta prime to be on the z prime, that is exactly equal to cosine theta. Same thing in here. This is r minus r prime, this is k per. If I choose this to be on the x-axis, this is literally cosine alpha, but otherwise in general I have a k per, that is the magnitude, and a cosine alpha. Cosine alpha is the angle between k per. It's not there in this diagram. This is r minus r prime, right? So r minus r prime could be in another direction. So that's your alpha. This is phi, let's say. That's phi prime. And a part will have its own angle. Correct. So this is your angle between the two directions. Let me also, for compactness, call this P. Just for compactness, if there's nothing significant in there. So I have my 1/4 pi integral with all that picturization, visualization, motivation. This is equal. This is two integrals in K. I want to do this in cylindrical coordinates, 0 to infinity, k per times dk per times d alpha, 0 to 2 pi. Right? This is a radial vector for k per, and this is the angular coordinate with in cylindrical coordinates. Remember, so you have cylinder, that's your two circles. And if you had to have an area element in here, so that's your area element. This is dr, and this is r times d phi, usually you say. This is r times d phi. So r dr d phi is your area, d cube. area. Infinitely tiny area. Here we are in the K-perp space. So if this was K-perp, so you would say K-perp, D K-perp times D alpha. So that's what we are talking about. This is instead of position vector, we are having D2 K-perp as your area. And then you have this, and I have, I lost a 2 pi there, right? This was a 2 pi square. I think I messed up. So this is 2 pi square. So keep a 2 pi here, keep a 2 pi there. And I have the exponentials coming out as I K per T cosine alpha times exponential of minus I K per Z minus Z prime and Q K per.
Should there not be an I on that Z minus Z prime there?
Oh yeah, that should be no Z prime because there was sorry. Bad mistakes. Yeah, those are bad mistakes. Yeah. Sorry. Yes.
Should there also be on the dot R and dot R prime? Should we say that those are one line above? On the line above that, should those R's be put in H2?
Yes. Thank you. Yeah. Bad, very bad. Yeah. It should be kind of more powerful. Yes. I think I'm thinking too much of what to say and not concentrating, but that's not an excuse. Shouldn't be. Yeah. Anything else you can point out? Be careful when you're seeing the videos because this comes 20 minutes down the line, so this correction doesn't happen in the video. Okay, but that's I think you guys know how to do it. Okay, so if I were to read, I think at this point I can erase this. Almost there. In minutes, K per pi can cancel out, and so let me write this as 0 to infinity. Let's also remove the 4 pi minus r prime. I can get rid of a 4 pi. There is a 2 pi and a 2 gone. K per cancels out. K per 0 is 5. The alpha pi and e raised to I K per p cosine alpha. That's the only place where alpha shows up. Right? This integral can be, so there is, for example, this has K per in it. So I cannot do the K per integral easily in general. But here there is only cosine alpha showing up there. So you've sort of isolated your alpha integral, alpha contribution in there. And what is that integration equal to? So this is of the form. So this integral is 0 to 2 pi. So angular integration, E alpha, 2 pi, let's say e raised to it cosine alpha. What is that equal to? Do that integral. An exponential. 0. No. What will it depend on? So if this is a function, f, what will it depend on? T. That's the only thing it will depend on. Alpha is gone. So find that function, do that integral. It's deceptively simple. This cannot be done.
I was about to say you get a 1/0 minus 0.
No, there is no divergence here. There shouldn't be any divergence.
Well, integral of that value, d alpha, you get 1/I t sine alpha, evaluated from 0 to 2 pi. Sine of 2 pi is 0, sine of 0 is 0. So you get 1/0.
It's not because I know the plot. I see what you're saying, but all that will cancel out.
Okay.
Yeah. So this cannot be done. There is no solution for this. So whenever you don't have a solution, you create a function for that. That's the Bessel function. Right? This is a Bessel function. So this is a function that is a t dependence to it. If you can solve that integral, good. Then you have a compact form for d0t. But you don't have that. So this is called the Bessel function. Of zero order. The way it is defined, it's clear that there must be an other orders too. First order, second order, nth order. In fact, the m itself in this will be, we will immediately say it is m, then we will have integral orders, then we will have continuous order. All that is a further extension of that, but this is the fundamental, the first Bessel functions you can think of. Is it, we don't even know whether it is real or complex. Is it real or imaginary? Can it be complex? Yes, because there is an explicit I showing up on the right side. So immediately we ask, what is the real part of this? Like there was a suggestion made that there might be divergence in this. This seems like when you do that integral as an exponential, there will be a divergence. So let's look at that. So let's look for what is, let's start with the imaginary. Is it real or not, right? So let's do the imaginary part of J0 of t. So that's equal to imaginary part here. It's relatively straightforward. So you can say this is 0 to 2 pi d alpha over 2 pi exponential of it cosine alpha. And imaginary part is, how do you do that? So you subtract, right? So you subtract minus the imaginary part in here, is that correct? Like z minus z prime. Is your imaginary part? Did I do that right? Think so? So it's cosine, right? So this is equal to 0 to 2 pi e alpha over 2 pi and or 1/2 is also there. Cosine of t times cosine alpha. Cosine is a even function, so we want to use that feature. So let's split this maybe. I think so. Let's try this. So 0 to pi, the alpha over 2 pi times cosine of t cosine alpha plus 1/2 of pi to 2 pi is alpha 2 pi times cosine of cosine alpha. I want to substitute maybe. So let's say on the second integral, I substitute alpha prime is equal to, like, cosine function has this feature that cosine of 2 pi minus something is the same as, like, cosine function has this integral, right? So this is 2 pi, that's 0. So this is always equal to, so 2 pi minus theta, right? So it is 2. So let's substitute 2 pi minus alpha. and alpha prime is equal to 2 pi minus alpha. So d alpha prime is equal to minus d alpha. So the second integral alone becomes plus 1 by 2. When it is pi, 2 pi minus alpha is 2 pi minus pi. So that's pi. And 2 pi minus 2 pi is 0. D alpha is minus d alpha prime over 2 pi. And here we have cosine of t of cosine of 2 pi minus alpha is cosine alpha itself. Oh, what did I make a mistake? There's a mistake here. Why did you do that? No, this one goes this to this. What's the definition of cos in terms of exponentials? Yeah, but exponential minus exponential divided by 2 is?
That's sine.
Sine, correct? Not cosine. So I should have done sine. My bad. And there is an I. Good, right? So there's an I also. So I'll put a I and an I. So this is I by 2 and a sine. Sorry about that. So that's sine, and then I don't think I should be substituting this at all. Sine of pi minus alpha is pi, so then I would do alpha prime is equal to pi minus alpha. So then this would be plus 1, and then there is an I everywhere. So so this is I by 2. When alpha is equal to pi, this is 0. When alpha is equal to 2 pi, it is minus pi. Sine of but now it is 0. So what do I substitute here? Again, 2 pi minus alpha. So 2 pi minus pi is pi, 2 pi minus 2 pi is 0. Yeah. And then this is minus alpha prime over 2 pi. Sine of 2 pi minus alpha is minus d of this remains the same. D cosine alpha because inside there is a cosine. So that's the difference. So that is a
Yeah, your bounds should be pi to 0. They should be. Oh, yes, they should just be.
Oh. What do you say? This is part. Okay. So sine of t, the sine of 2 pi minus alpha prime. Sine of 3 pi minus alpha prime is the sine itself. That's how about this? Maybe alpha plus 2 pi?
Technically not.
Alpha. How can that be wrong?
Everything has to. Yeah, there should be a minus sign there because when we put the limits of integration, minus has to cancel.
So this much is okay. Let me go back to here. Okay. Oh no. Quiz. Evaluate So what is this equal to? This is all you have to do. I think you have to do the right substitution, and either this will cancel out or this will add up. And somehow it lost it. One more thing I want you to check is what is limit, because this case, so this is first. Second, what you want to show is, since this was brought up, what is limit t tends to 0 of k0 of t. That you can sort of see it right away here. So if you set t equal to 0, what is that? We give 1. So it's short from 1, so there is no divergence at t equal to 0. So this one. And we'll start from here next time and explicitly do properties of Bessel function. Again, differential equation for Bessel function, completeness for Bessel function, orthogonality for Bessel functions, and addition theorem for Bessel function. These are the fundamental quantities. Sorry about that. Yeah. Throws me off. Yes.